So in neutrino physics, we are entering the precision era. Now it has already been established that the neutrino oscillate, and therefore flavor eigenstates and mass eigenstates are not equal, but the flavor eigenstates are a mixture of the massive neutrinos. And this mixture is given by the electronic symmetric, or the commonly referred as Pimenez matrix. That is the analog in the quark sector of the CKM. And as you can do also in the quark sector, this electron symmetry, you can parameterize it with 3 angles and 1 CP violating phase. And in the last decade, we have had a lot of data, and this data has allowed us to precisely measure many of these oscillation parameters. So the theta 1,2, theta 1,3, theta 2,3, they are measured to the percentage level, and also we have distinguished 2 different mass splittings. One that is the smaller one, that is of the order of 10 to the minus 5, that is called the solar mass because it is involved in solar neutrinos, and the other one that is larger, that is usually called as atmospheric mass splitting because it enters in atmospheric experiments. Okay, this is what we know, but there are still several things that we do not know yet. Basically, we don't know those quantities that require a lot of precision in oscillations, and those would be the deltaCP. Right now, the deltaCP, we don't really have a precise measurement. Also, the mass ordering. I said that there are 2 mass splittings, but you can accommodate this in 2 different ways. Basically, you can either have normal ordering, that is having a heavy neutrino, I mean, heavier than the others, and then 2 that are lighter, and this is what you should expect in most cases, so this is usually called normal ordering, and the other one that is inverted ordering, in which you have 2 heavier ones that are very close together, and then a third one that is much lighter. And this is inverted ordering, and typically right now the oscillation experiment, they give you a preference for normal ordering that is around 2 sigma, but still inverted ordering is not excluded. Also, the theta 2,3, we do not know yet the octant, so it could be more than 45 degrees, less than 45 degrees, we do not yet that. And this is respect to oscillation, but there are other things in neutrino physics, like the absolute neutrino mass scale that we don't know, and whether neutrinos are Dirac-Majorana is also an open question. But in this talk, I will be concentrating on oscillations, so I will forget for the moment the absolute mass scale and the nature of neutrinos. Okay, so now, so in the past we have had a lot of data, but now in the future, in the coming decades, there is also a lot of data that is coming. For example, for the new long baseline experiment like DUNE in the US and Hyper-Kamiokande in Japan, well, they will start taking data in the coming decades, and we expect a lot of information from them. Also, Juno very recently has started releasing data and is giving very promising results. And we also have other big experiments like AIM3net in Europe and IceCube in the Antarctica with the new generation of IceCube that it will also be contributing. So in brief, we will have a lot of data, and that can really, or we hope that it will allow us to measure the remaining pieces of the puzzle. Okay. Oh, sorry. So for the first part, I will focus on CP violation. So let me give a very brief review. So CP violation, you can understand it as asymmetry between neutrinos and antineutrinos. So if you know that any quantum field theory needs to be CPT conserving, and if you apply a CP transformation, you go from the probability of neutrinos to the probability of antineutrinos by flipping the sign of delta CP. So if you are in the CP conserving scenario, then these probabilities in vacuum would be the same, and if you are in the CP violating, they could be different. Also, there is okay, what is the reason why we haven't yet detected delta CP? Well, there are several reasons, and we will discuss them. But the first is that if you go into the probability, the delta CP is contributing at a subleading or at a second order. So you need really precision to measure it. So basically, if you see how delta CP enters in the probability of oscillation, you see that it's suppressed with this ratio of the mass splittings that due to the fact that this mass split is much smaller than the second one, it gives you that the contributions are second order. Okay, they are not necessarily very small, but they are second order, so they are not the leading terms. And another thing is that we have seen that this CP would make neutrinos and antineutrinos oscillate in a different way in vacuum. And then you would think, okay, then we can try to detect this asymmetry. But the fact is that the asymmetry is not only coming from CP, it's also coming from matter effects. Basically because ordinary matter is made of matter and is not made of antimatter. So just because of that, then, when you include matter effects, neutrinos and antineutrinos also propagate in a different way. And well, if you really want to know that you are measuring delta CP, you need to distinguish also delta CP from matter effect. Okay, so that's from the theory point of view. But now let's go to what we really measure. So I've been talking about probabilities, but do we really measure probabilities in an experiment? So in an experiment, how you measure neutrinos is in the following way. So basically, neutrinos are like ghosts. So they enter your detector, and all of a sudden you see an interaction inside the detector, and well, the only thing that can produce that, at least in the standard model, would be a neutrino. And now, depending on the flavor of the neutrino, it will produce by charge current interaction either a muon if it is nu-mu or an electron. So, but if you see a lepton in the final state that is a muon, then you would say that this event is like a nu-mu event. And if you see an electron, then it would be more like a nu event. Okay, so this is what you see. Now, if you really want to start the probability, what you see is on the left-hand side of this equation. But you want to start the probability. The thing is that to compute the number of events, you need to put in the flux, the initial flux of neutrinos in the flavor alpha, then the probability of that flavor to oscillate to the flavor beta that you are detecting, and then the cross-section of detection. And then, well, there are also other functions that relate the true energy and the energy that you actually measure at the detector, because they are not exactly the same because of detector effects. But already with this flux and this cross-section, the problem is that in many neutrino experiments, these are not very well known, and they have large uncertainties. So if you want to very precisely measure this probability, well, you start seeing that this is not so easy, that inverting this equation to start the probability is really quite a difficult thing to do. Okay. Now let's go to a very specific type of experiment that are the long Veilam experiments. So there will be two future long Veilam experiments, will be DUNE and Hyper-Kamiokande, and they will promise us that they will measure delta CP. So let's understand a little bit how these experiments work. So basically what you have is you have a proton accelerator. From this proton accelerator, you collided the protons with a target, and from this collision you produce mesons, mainly pions and a small percentage also of kaons and other mesons. Then you focus these mesons because you want to detect neutrinos very far away. So you want your flux to be really, really collimated. Otherwise, you will lose most of the flux and you will not see anything. So that's why you need to focus it. And then there is an empty space that is called decay tunnel or decay pipe, where these pions and kaons, they decay. And just because of the branching ratio that you have, most of the neutrinos that are produced in this setup are nu-mu neutrinos. Then these nu-mu neutrinos, they get out of the decay tunnel, and they are detected in two different places. In a near detector, very close to a source, so these new moves don't have time to change flavor, and then very far away where they have changed flavor, and then you try to measure the oscillation. Okay, then why in this type of experiment we need two detectors? So that is what we're going to understand in the following slide. So let's see what are we really measuring in each detector. So in the near detector, you have the flux of new moves. The probability, since you are very close, is just 1. There's no time to change flavor. And then you have, since most of the neutrinos in the near detector are new moves, you have the cross section of new move. Okay, this is at the near detector. At the far detector, you have also the flux. Then you have, if you measure in the appearance only, you try to measure nu, you have the probability of going from nu mu to nu, and then you have the cross section of nu. The thing is that imagine that there is no near detector. Then you have this equation. And I already told you that the fluxes and the cross section, they, in this particular type of experiment, they have large uncertainties. So inverting this, it would be almost impossible if you don't have a near detector. And why? It's because instead of relying only on the event rate of the far detector, what you will do is the following. You have two measurements and you do the ratio between them. Because if you do the ratio, the quantities that appear here are basically the ratio of the fluxes that are not exactly the same because of the geometry. Basically, if you are very close to a source, you would cover more angles than if you are very far away, and that would change a little bit your energy. But apart from that, you expect to have a similar flux. And then there is an important thing is that you have here the ratio of two different cross sections. That is the cross section of nu and the cross section of nu. Here, to extract the probability, they do an assumption. And the assumption is that they assume that you have lecture universality, and under this assumption, the only difference between the cross section of nu and the cross section of nu could be due to nuclear effects, and if they have models in which they estimate that this is around 3%. So they use these models and these generators to try to predict the cross section of nu from the cross section of nu that they have measured at the near detector. And with that extrapolation, with that assumption that they make, then they can extract the probability with high precision. The problem is that, okay, they rely on a theoretical assumption and also on the validity on all these models. So there is some modeling there that you need to believe, and otherwise is difficult to proceed. Okay, so that is the assumption. Now, but this assumption could be having already an effect in the current data that we see. So let me put you an example. So right now, the main experiment that try to measure deltaCP are also non-baseline, are T2K and NOvA. And the thing is that T2K and NOvA, if you take the data independently, they both prefer normal ordering. But they prefer it with a value of deltaCP that is not compatible among them, and they have a small tension at the 2 sigma level. Basically, NOvA, they prefer this region that is compatible with deltaCP CP conserving, so deltaCP 0, and T2K prefer large values of deltaCP. Okay, now if you try to compare how these two experiments work, you realize that first they rely on different ways, different neutrino generators to do this extrapolation and to predict the cross section of nu. So in T2K they have NEWT, and in NOvA they have Gini. Also they have different materials. So the detector one is Warre-Cherenkov, and the other one is a carbon liquid scintillator. And also the energies of the neutrinos, the peak of the fluxes are quite different. So in T2K is 0.6 GeVs, and in NOvA is 2 GeVs. Then there are several possibilities for this small tension. One way, okay, maybe it's just a statistical fluctuation and this tension will go away. Okay, that's a possibility. It has happened in the past. It could, I mean, it could go away by itself. It has been there for quite a long time, but it could go away. That's true. Also, there are some people that say that this might be a hint of new physics. There is some new physics that is affecting one and not the other. And, well, you can find in the literature explanations that, that try to explain it in that way. For me, maybe it's a little bit too early because it's only 2 sigma. What I think it could be happening is another possibility is that they have a systematic bias. Basically, is that the assumptions that they are doing are not really compatible with each other, and these might be biased them to different values of delta CP. Okay, that's also another possibility that we don't know. We don't know if either of these three possibilities, if this is these ones or something else that we don't know. Okay. Now, now let's go again to the future. So if you go to T2 Hyper-K and DUNE, what did they promise us for the delta CP? Under the assumption that I explained that you need to rely on these simulators and the electron universality and all this. So if you do all of that, what they tell us is basically with these what they call McDonald plots, because they look like McDonald. This here you see the significance versus delta CP, and what this plot means basically is that if you have a delta CP value that is, for example, this value, you will be able to distinguish it from a CP conserving case with the significance that is given by this plot. And what you can see is that for many of the values of delta CP, you should expect for both DUNE and T2 Hyper-K to have more than 5 sigma discovery. Okay, this is what they promise us. But could history repeat itself? So we already have attention with T2K and with NOvA. Could this again happen with DUNE and T2 Hyper-K? Well, the thing is that we cannot really be sure. And to try to understand if this is really a possibility or if it is just or not, let me play the following game. What happens with the sensitivity that we have just seen if we try to be completely agnostic? And by completely agnostic, I mean not relying on this on trying to obtain the cross-sectional NUI from data of cross-sectional NUMU. If we try not to rely on this, then if we don't rely on that, we need to rely on data. And then you go to the literature and you see the data that we have, you will see that this is very asymmetric between the electron sector and the muon sector. So in the muon sector, you have quite a few points, data points. So it's relatively well known. I mean, it could be better, but you have at least you have some data. But for the electron sector, you only have very sparse points with very large error bars. So what we play is, okay, let's put a cross-sectional NUI that is compatible with this data of NUI, but we don't put any other requirement, only that is compatible with the data. And then, since you have only a few data points, then you can have cross-sections that can do many different things, and it's still allowed by data. And what we want to see is, if we do that, how much of the sensitivity is lost. Because if we see that, we will be able to see how much of the sensitivity comes from the data and how much comes from the assumptions. So by doing that, you see that, okay, the red is the analog of the ones that I saw before. So that is taking all the, relying on simulators and on theoretical assumptions. And the blue is only relying on data. And what you see is that you lose half the sensitivity. That is quite a lot. I'm not saying that these assumptions are, that we shouldn't take these assumptions that are crazy. I'm not saying that. I'm just saying that we need to know and we need to be aware that half of the sensitivity comes from the assumption. even if those assumptions are okay, but they come from there, and if there is something wrong there, then that would enter into the game. Okay. So now, what is the possible solution to try to have a more robust deltaCP determination? So this will come from, we explore the possibility of this proposed experiment that is called nuSCOPE, that is designed to measure very well fluxes and cross sections. So this nuSCOPE was proposed last year. It will be located, if it is really approved, it will be located at CERN, and it will make use of what is called the program of starting beam lines. Let me explain a little bit what this is. So you know that at CERN we have the LHC, but next to the LHC we have the SPS. So the SPS is a circular accelerator that provides 400 eV protons to the LHC. But apart from that, this SPS is used to produce many secondary beam lines that are used in many different experiments. For example, some of these experiments are located in the north area at CERN. Basically, all the experiments that you see that start with an NA62, NA64, all of these, they are located in this north area at CERN. And it's in this north area at CERN where they want also to place this nuSCOPE experiment. So nuSCOPE, it will measure cross sections in several ways. So let me explain the first technique that they use, that is what is called neutrino tagging. So with neutrino tagging, what you do is the following. So as before, you have a target and then you have protons or that collide here and produce mesons. Then first you have a detector that measure the momenta of the pion. Then you have a decay tunnel where these pions decay, and then you measure the lepton. Okay, so you know two things. Sorry. You know the pion momenta, so the kinematics of the pion and the kinematics of the lepton. And since this is a two-body decay, you can know already the kinematics of the neutrino. So from these two measurements, you know already the kinematics of the neutrino. And then in a neutrino detector, you try to search for this neutrino. And if there is a coincidence, then you take that event and you have a complete event in both production and detection. So you have all the variables possible. And this way you can decouple the cross-section and the flux. Because as you saw before, the cross-section and the flux are always together. It's very difficult to decouple it, but with this technique, you can decouple it. There is a caveat. The caveat is that you rely on this two-body decay, because two-body decay is very simple kinematically. So this allows you to only measure with this technique very well the cross-section of NUMU and the neutral current cross-section, because basically it comes from the NUMUs of the two-body decay. But in the case of the cross-section of NUI, it's more difficult because most of the NUIs are produced from kaons and via this three-body decay, and then just by measuring the kinematics of the kaon and the kinematics of the lepton, you cannot know exactly in an event-to-event basis the kinematics of the neutrino. Okay, but okay, what we wanted really is to measure this cross-section of NUI, because it was really what was causing a lot of trouble. So, okay, not everything is lost, because there is another technique that they use. And this second technique is called the combination of the PRISM and the narrow band of axis technique. Okay, so what is this? So basically, as before, you measure the momentum of the kaon and you measure the lepton. By doing that, you cannot know exactly what is the energy and the kinematics of the individual neutrino in that particular event. But statistically, you can know what is the function of the neutrino flux as a function of energy. Not in an event-to-event basis, but in a stochastic way, you can really induce it. So you will know this function from this. Now, if you go to the detector, they do this very interesting technique. They take the detector and they split it in different cells, because if you go to a very small cell, then each small cell, they will see in this two-body decays of NUMUs an almost monochromatic line. And if you split it in small enough cells, you will have a lot of fluxes of NUMUs that, since they look almost like a chronicle delta, they form a pseudobasis. And if they form a pseudobasis, that means that by the definition of what a basis is, that you can span any other flux as a function of them, and any other flux is just a linear combination of them with certain weights. And one thing that you can do is, okay, you already know, you have measured the flux of NUI in a stochastic way. Now, let's try to find the coefficients that make this equality true. Okay, and then, okay, why should we do this? Why is this important? Because then we find these coefficients, this allows us to build this quantity that I call here the NUMU virtual events. And this is going to allow us to do the following. If you think of the meaning of this NUMU virtual, it could be basically, theoretically, could be the convolution of the flux of NUI times the cross-section of NUMU. You see that typically when you go to any experiment, what you have is not this. Is you have the flux of NUMU times the cross-section of NUMU, but not the flux of NUI times the cross-section of NUMU. This is a different thing, and that's why it's called virtual. It's not really what people call the number of NUMUs. But if you build this observable, you can do the ratio between the number of NUI events and the number of these NUMU virtual. And they claim that they can measure this ratio with 2% uncertainty, a very precise measurement of this ratio. And this what allows us is the following. You see, in this ratio, the cross-section of NUMU we have already measured from neutrino triangle before. The flux of NUI we know stochastically, so the cross-section of NUI, it cannot really move a lot without affecting the ratio. So that means that by measuring this ratio in this way, you can translate many of the small uncertainties that you have in the flux and the cross-section of NUMU to the cross-section of NUI. So this is a very powerful way to constrain in an indirect way, but a very powerful way to constrain the cross-section of NUI. Okay. So now let's do that. Let's apply, apart from the what happens if we assume that we have done this nuSCOPE measurement, what happens to the sensitivity. So what you see is that now the blue curve is almost the same as the red curve. So you have recovered almost all the sensitivity. But now this blue curve is a very strong determination of deltaCP that does not rely on lead to universality, does not rely on relying on simulators. It relies only on data. So it's a very robust. And the thing is that imagine that we have a tension in the future between T2 Hyper-K and DUNE. If we don't have a robust determination, we cannot know if it is new physics or if it is another effect that is coming from the cross section. But if we have a very precise determination of deltaCP, if there is a tension, well, we can avoid the tension. And also, if there is a tension, we will know that this cannot be. That there need to be other things, possibly physics or other things. But there is not a degeneration between new physics and the assumption that we do for the cross-section anymore. Okay, so that was the main point. So that's the first part of the talk. And now let's go to the second part. So for the moment, it was all like a standard three-neutrino picture. So what about if we try to measure new physics in oscillations? So what type of new physics you can expect in oscillations? There's two benchmarks that people usually explore is non-unitarity and stellar neutrinos. Both non-unitarity and stellar neutrinos, they appear, well, I mean, when you try to explain the small neutrino masses, or you try to have a model, it's very typical that in that model you have heavier neutrinos than just the 3 neutrinos that you need for oscillations. So in all generality, you would expect that you have more than these 3 neutrinos, and then in all generality you will have n neutrinos. And if that is the case, then the leptonic missing matrix now is no longer 3 by 3, it's an n by n matrix. And this n by n matrix, general leptonic missing matrix, would be unitary, but the subblock that relates the flavor neutrinos with the light neutrinos doesn't have to be unitary, basically because of the existence of these other rows of the matrix. Okay, so now let me explain, because there is some confusion, and sometimes when people talk about non-unitarity in two different contexts. So if you go, for example, to the global fit of non-unitarity, they tend to talk about a non-unitarity of this fashion. So I will call non-unitarity when you have heavy neutrinos that are larger than the electroweak scale. If they are larger than the electroweak scale, then basically you can integrate it out of your theory, and at the end you have like the standard model Lagrangian, but instead of having the P-S, that is a unitary matrix, now you have this submatrix N that doesn't have to be unitary by construction. But this can affect, the fact that this matrix N is non-unitary can affect many different observables. For example, one observable that it can affect is muon decay. So the muon decay, that is the observable from which you extract, for example, G Fermi, now it will also be affected by this combination of the N matrix. So when you think that you measure G Fermi, in this scenario, you will not be measuring G Fermi alone, but G Fermi and this other combination of the N. Also, the fact that it's non-unitary appears in lepton flavor universality tests. It also appears in the invisible decay of the width of the Z. It appears in many different places. And if you do a global fit, for example, like the ones done here, you see that the deviation from unitarity is very, very well constrained up to the per mil level. So it's really very, very well constrained. Now, also, this if there is no unitarity, this will also affect neutrino experiments, because these heavy neutrinos, they cannot be produced in the beams of the neutrino beams, and then when you try to compute the oscillations, instead of doing it with this P-S matrix, you will do it with this other subblock that is a non-unitary subblock. And people usually to parameterize the deviation from unitarity, there are several parameterizations in the literature. One of these is this one. So basically, here when the alphas are equal to 0, you recover unitarity, and when they are different from 0, then you have a non-unitary matrix. And the most common place to look for these effects is at very short distances, because at very short distances, in the standard case, you don't expect any oscillations, because they don't have time to develop. But because you don't produce all the neutrinos, then you will see already effects at very short distances. But the caveat is that even though there are effects in oscillations, since these deviation from unitarity are very strongly constrained by electroweak precision data, then you don't expect to see anything in oscillation in this type of non-unitarity. So, but people still talk about non-unitarity in oscillations, and it's not because they are wrong, it's just because they will talk about other type of non-unitarity that is going to be the non-unitarity that I will introduce next. So now let's go to a stellar neutrino. An stellar neutrino, usually the typical assumption is that the mass is not very high. It's like below 1 keV. And in this case, there is not any constraints from electroweak precision data because all of them are produced, all of them are basically massless. And if you see all the observables that I saw before, you will recover the same prediction and the standard model. So you don't have these very strong constraints. But these stellar neutrinos, then they will be able to be produced in long wavelength experiments, for example, or in other experiments. And the main bounds that you get come from oscillations. And people get interested in these stellar neutrinos because there were some anomalies. Some of them are still there. For example, the anomalies of the LSMD and the minimum that, well, not many people nowadays believe in these anomalies because we have had microboom to try to test it and they haven't seen anything. So it's really, we do not know what happened with this experiment, why they were seeing this stellar neutrino. Now, for the rest, I will focus on a very specific case of stellar neutrinos, that is what you usually see in PHENO analysis, where you only include one stellar neutrino. So if you only include one stellar neutrino, then it's very simple how you compute the probabilities. Is instead of using the standard PMS, you use this 4x4 matrix. And if you look very close to the neutrino source, then the standard oscillation don't give you any contribution, and the only contribution comes from this stellar neutrino, from this 4-1 mass splitting. And they take the form that is very common of the two family approximation. So they take very simple expressions. In the case of appearance, it depends on both flavor mixing, and in the case of disappearance, it depends only on one flavor. And now, but there is a limit that you can take in stellar neutrinos. And this limit is, okay, what happens if you take this stellar neutrino to be more massive? Still being produced, but being very massive. If it's very massive, at least for oscillations, these signs, they will start oscillating very fast, and you will not be able to resolve it in an experiment because you have a finite energy resolution. So what you will see is just an average. So in this limit, basically these signs, they just average out to 1/2, and what you have is just a constant deviation from the unitary case. So this is, this is just a plot where it shows the average out limit, so it's just a constant. So this constant behavior is basically the same thing that we have in non-unitarity that I just saw before. It's just that it's in different parametrizations. Before we have the alpha parametrization, and here we have the mixing. But the phenomenology is the same. So it's also useful to put it in the same parametrization to see if there is any difference. So if you map the alpha parametrization with the mixing, you will see that the difference is basically a factor 2 in appearance. So in this average out limit, you just have a factor 2, and in this appearance at linear level, there is no difference at all. So this average out limit of the steriles is what some people call also a low scale non-unitarity, and is where neutrino experiments might have something to say, because as I already mentioned, the other case of non-unitarity with heavier neutrinos, that is constrained from electroweak. So it's only in this low scale non-unitarity in which oscillation experiments can have something to say. Okay. So now, where you will look for this? One way is at near detectors, and in particular, in the second paper that I presented at the beginning, we focus on the DUNE near detector. So we already know that it's a long wavelength experiment. We already know how it works, and there is a near detector complex where you have a detector that is a liquid argon TPC, but it's not really important, that is called NDLR, and it will be the detector that we'll be using. But the problem is, again, systematics. So how systematic uncertainties affect this? I mean, we already saw that they might have an effect in the deltaCP, but what about new physics? Well, new physics is much worse, I would say. Why? Because basically, what you're trying to see, so this type of sterile and non-unitarity effects, you see at the near detector. But at the near detector, you have already from the standard model thousands of events, of neutrino events, many neutrino events. And what you want to see is a small variation on that. And the only handle that you have is that your signal is different in the spectra from your background. So, okay, this is an histogram, the number of events versus the observed energy. This is the background that is huge. It's basically the standard model neutrinos interacting. And then this other in more solid is the expected signal that you will have in non-unitarity. And you see that it's much smaller than the background, but it has a very different shape. So the thing is that if there is a systematic on this shape, it will make the search very difficult. This is really important. So this was one of the goal to try to quantify this. So the last paper that I told you that I did a few years ago, where we see that it really affects the sensitivity by a lot. So basically, this is in the okay. This is a sensitivity in the plane of the mass splitting of the forest sterile versus this combination of the mixings. And for this combination of the mixing, you have contributions from both appearance and disappearance channels, because both the mixing with electron and mixing with the muon needs to be turned on. And if you go to the predictions or the naive prediction that were given at the very beginning, you saw that there was a very impressive sensitivity. There was this solid line here. But if you start putting this uncertainty on the spectral shape, then you see how the sensitivity is reduced a lot. Okay, so this was what we conclude in this paper. But now in the second paper, we want to try to put a solution to this and try to see if there is a way that we can mitigate this. And to do it, we're going to rely on something that they want to do at DUNE that is called PRISM. And it's very similar to the PRISM that I saw before with nuSCOPE, but it's slightly different. So before, it was just looking at different sections of the detector. Now it's not looking at different sections of the detector, it's moving the detector. So they're going to build the near detector in a complex where they will have some space to move. And the thing is, if you move it, then you have access to different opening angles. So, and that what it means is that as you go off axis, the energy of the neutrinos could be lower and lower in energy. This is basically because if the neutrino is very energetic, the opening angle that it has is very small because it's very boosted. And if the neutrino is not so energetic, then the opening angle is much larger. So that's why when you go off axis, you have access to lower energy neutrinos. So what we wanted to do in the paper is, okay, here the difference between the event rates that they will measure the detector in different off-axis angles could be just the kinematics. The cross-section will be the same. The flux is the same. It's just that you are moving and you are accessing different kinematics of the flux. So this that means that we can, in principle, correlate a lot of the systematics that are the main problem here. For example, the cross-section systematic is it's really a problem. But here we will have independent measurements at the same energy in different positions. So by taking ratios of these independent measurements, we can cancel a lot of these systematics. So that is the idea. And what happens? So if we do this, if we correlate between the different off-axis modes, we obtain the following. So this is from non-unitarity. So I'm here presenting the chi-square versus the alpha mu e. That is the parameter that controls the transitions of nu to nu e that will happen at very short baselength. And what you see is that if you take a large shape uncertainty, the DUNE prediction will be very close to the present bound. But if you consider this PRISM technique, then you will recover a lot of the sensitivity, and you will be having a result that is very similar to having a much lower shape uncertainty. Here in blue is just an optimization that you can do if you put more years in the first off-axis mode. So this is just an optimization. But what you should read from this plot is that if you put PRISM, due to this cancellation of systematics, you really improve, and you are expected to improve by quite a lot from current bounds. Okay, this is for non-unitarity. And now what happens from stellar neutrinos? So from stellar neutrinos, first in DAS, we took a value of the state that is somehow conservative. And if we are conservative in that side, then if we only use the normal near detector, and we don't use this PRISM technique, then we expect to be very close to the current bound. But if we use the PRISM technique as before, then we have a very strong increase in the sensitivity, and DUNE with this PRISM technique will be able to cover quite a extensive region of the parameter space. Okay, so now bring me to my conclusions. So here I have shown that the systematic uncertainties can be important, that they could be already be playing a role in the current neutrino data with already the standard oscillations. And also, if we want to try to measure new physics with the new experiments, especially new physics in oscillations, we really need to have it under control. And for these things like experiments like nuSCOPE, it would really be very beneficial. And also the other strategies that don't rely on having an experiment, but are things that individually each experiment can do, like the PRISM technique. It would also be very useful to try to extract as much as possible from this future data that we will receive. Okay, so thank you.
Thank you very much, Alba, for the very nice talk. Very nice and complete talk. Question from the audience?
Yeah, I have a question.
Yes.
Say, for example, like in DUNE, right? You have a beam of muon neutrinos that you want to see they convert to electron neutrinos, right?
Yes, most
Now, but you do have some contamination of electron neutrinos from the beginning.
Yes.
Is that important?
Well, yes. I mean, for example, I mean, it's important. You mean for what? For new physics, for example, for new physics?
Right. You want to detect, this
oscillation. Yes. So mainly for these means, you will have two backgrounds. One is that one, the contamination. But and another one, you also have a neutral current that can be misidentified with within NUI. So that those are the main two things. So intrinsic NUI contamination and misidentification. But the thing is that this intrinsic since they are produced from kaon decays, they have a different spectra than these ones, because these ones would be, since most of the NUMUs are produced in pion decays, they will have the spectra of the pions. So that's why there is a difference in the spectra between one and the other, because one is produced from kaons and another is produced from pions, and that is the handle that allows you to distinguish the one and the other. They will have a different energy because of that.
Yeah, but the pions also, they have a fraction of pions that decay into electrons, right?
No. At the near detector, no. At the near detector with the standard oscillation, you don't expect to have any NUMU. Okay, repeat the question. What did you say?
No. What I mean is that, yeah, well, you have a pion that converts into a muon and a muon neutrino, right? Because the pions decay mainly into muons and muon neutrino. But there is also a probability that the pion decays into an electron and an electron neutrino, which is much smaller. Yeah, but the question is that important?
No, I don't think it's helicity suppressed. It's very, very small. I don't think it's it could be the ultimate reducible back. Yeah, that is the background that you cannot take away. Yeah, but it's much smaller than the other one.
Yeah, that was my question. Okay.
Any more questions? More questions from the audience? Salva, when you were discussing the non-unitarity, the deviation from the unitarity, you show a parametrization where the off-diagonal entries were below the diagonal.
Yes.
What is the reason why it's not taken in the other way? It's just an answer, or there is some specific reason why this entry, upper of diagonal entries are taken to 0?
No, I mean, actually there are several parametrizations that in the literature, but it's just I mean, there is not. You can do it. I mean, if you put this in the other side, it would be with the upper instead of the lower triangle, the upper triangle. There is not really. I mean, it's just an assumption. Like you can parameterize in several ways, and they are all equivalent to each other. So it's not. It's not a big thing. It's just that any generic matrix, you can always express it as a unitary matrix and a lower triangular one, or an upper triangular one, depending on where you multiply it. So basically, this is a generic way that you can write it, but people write it in other ways that are equivalent. So.
I see. Thank you. More questions from the audience? If there are no more questions, we thank Salvador for the very nice and very complete seminar. Thank you so much, Salvador.
Welcome.
And we meet at the next seminar. Thanks a lot.
Thank you.
Bye.
Bye. Bye-bye. Bye. Thank you so much.